What would happen if GPS disappeared for 24 hours? At 8:17 on an ordinary Tuesday morning, Alex's blue dot stops moving. He has not stopped. The dot has. A second later, the delivery van ahead of him misses a turn. A cyclist pulls over to stare at a frozen map. At the airport, cockpit systems lose one of their most trusted references. In a nearby field, a tractor drops out of automatic steering. And inside a data center, a precision clock quietly switches to backup.
Nothing explodes, no warning appears in the sky. But for the next 24 hours, one of the invisible foundations of modern life is gone. So, what actually happens? First, one important detail. GPS is technically the American satellite system. Galileo, GLONASS, and Beidou are separate systems, and many modern phones can use several of them. If only the American GPS constellation disappeared, some devices would simply switch to another one.
So for this thought experiment, we will use GPS, the way people commonly use the word. Every satellite navigation signal that normally gives our machines position and precise time has vanished worldwide for exactly 1 day. An outage this broad is extraordinarily unlikely. There is no single satellite or cable whose failure could erase every global system at once. But imagining the impossible reveals something real. Many services that appear independent are quietly built on the same signals from space.
The internet still exists, roads have not moved, downloaded maps remain on phones, airplanes can still fly, and clocks still tick. What disappears is the easy, automatic answer to two questions. Where am I, and exactly what time is it? GPS satellites normally broadcast one-way radio signals containing their position and extremely precise time. Your receiver compares signals from at least 4 satellites and calculates where it is. The satellites are not tracking Alex. His phone is listening to them and doing the math. When those signals vanish, the first hour feels more confusing than catastrophic. Some phones estimate their location using cell towers, nearby Wi-Fi networks, and motion sensors. In a dense city, Alex's blue dot may still appear, but it could jump between streets or drift away from his real position. In rural areas, it may disappear completely. He can still view a map. He can even type in a starting point and read a route. But reliable turn-by-turn navigation, live location sharing, fitness tracking, geofences, and Find My Device services become uncertain. Rideshare drivers struggle to locate passengers. Couriers cannot trust their next turn. Fleet managers see trucks freeze in place on their screens. Public transportation does not stop either, but passengers lose accurate arrival estimates and operators lose part of their live fleet picture. Buses still know their assigned routes and trains still follow tracks and signaling systems. What disappears is much of the precise coordination layered on top, where each vehicle is, whether it is late, and how quickly the network should react. Most drivers do not become helpless. They follow signs, ask for directions, or use roads they already know. But enough people slow down, miss exits, and stop in unsafe places to create new congestion. A tool designed to save a few minutes begins wasting millions of them at once. Emergency response becomes more difficult too. Phones and dispatch systems can use more than GPS to estimate a caller's location, so emergency services do not go blind. But accuracy can become worse, especially outdoors, on highways, or in remote areas. Callers must describe street names, intersections, buildings, and landmarks. Ambulances, police cars, and fire crews still respond, but finding the correct place may take longer when every second matters. Search and rescue teams face the same problem on a larger scale. A missing hiker cannot send a reliable position. Aircraft and boats must search wider areas using radio direction finding, maps, landmarks, and human observation. The rescue remains possible, but the search zone becomes much bigger. By the second hour, airports and control centers are already operating under backup procedures. Commercial airplanes do not fall from the sky when satellite navigation disappears. Pilots can use inertial navigation, ground-based radio beacons, radar, instrument landing systems, and instructions from air traffic control. But those backups are not as flexible or efficient everywhere. Some satellite-based approaches become unavailable. Aircraft may be given longer routes, arrivals are spaced farther apart. Airports with fewer ground-based alternatives may accept fewer flights, especially in poor weather. Delays grow, diversions begin, and some departures are canceled before the system becomes overloaded. The same pattern appears at sea. Ships still have compasses, radar, charts, depth sounders, and trained crews. In open water, many can continue cautiously. Near a crowded harbor, however, precise position matters much more.
Port authorities may increase the distance between vessels, delay arrivals, or keep ships waiting offshore rather than risk a collision in a narrow channel. Railways are less visibly affected because trains cannot wander away from their tracks. Core signaling and braking systems do not simply vanish, but dispatching, maintenance crews, cargo tracking, and passenger information can lose accuracy. Once again, the system survives by becoming slower and more conservative. Nothing has stopped moving. Everything has started moving more slowly, with larger safety margins and more humans making decisions.
On land, the outage reaches machines Alex rarely thinks about. Surveyors cannot make precise measurements, construction crews lose satellite-guided machine control, container yards have more trouble tracking equipment. Some drones return, land, or refuse to launch when they cannot verify their position. On farms, GPS-guided tractors can normally follow extremely accurate paths through darkness, dust, or fog. Without that guidance, automated steering and precision spraying may pause. Farmers can still work manually, but overlapping one row and skipping the next wastes fuel, seed, fertilizer, and time. A 24-hour delay during an ordinary week is inconvenient. During a narrow planting or harvesting window, it can be expensive.
Then comes the part most people never see. GPS does not only tell machines where they are, it tells them when they are. The satellites carry atomic clocks, allowing receivers around the world to share time with astonishing precision. Cell networks use precise timing to coordinate base stations. Financial systems use it to order and record transactions. Power companies use synchronized measurements to observe disturbances moving across the electrical grid. Imagine an orchestra whose musicians can still play, but whose conductor has suddenly disappeared. For a while, everyone follows the rhythm they remember. Then tiny differences begin to grow. Critical systems prepare for this with holdover clocks. When the satellite reference vanishes, a local oscillator keeps producing time. A high-quality atomic clock can remain accurate far longer than a cheap backup. That means a GPS outage is not one giant switch turning everything off. It is thousands of smaller countdowns, each depending on how well someone prepared.
Most well-designed phone networks would probably survive a single day. Fiber connections and strong backup clocks keep important parts synchronized. But resilience is uneven. Some poorly equipped or remote sites could lose accuracy sooner, reducing capacity or causing patchy service. Calls may still work, while data becomes slower or less reliable. Engineers may disconnect unstable equipment before it interferes with the rest of the network. The internet does not switch off at midnight either. Large data centers often have several timing sources, disciplined local clocks, and connections to other reference systems. Ordinary servers do not all require atomic clock precision, but services that compare events across distant machines become harder to trust when their timestamps drift apart. Logs can appear out of order, automated checks can fail, and investigators can struggle to reconstruct exactly what happened first. Banks do not suddenly forget how much money everyone has. Cards do not all stop working at the same instant. But precise timestamps matter when enormous numbers of transactions happen in fractions of a second. If two systems begin disagreeing about the order of events, software may flag records, slow automated activity, or suspend a service until trustworthy time is restored. The problem is not that time has stopped. It is that machines no longer agree on the same now. The electrical grid is similar. Electricity does not require GPS to flow through a wire. Local protection systems and generators keep operating. But synchronized sensors help operators understand where and when a disturbance occurred. Without that shared reference, parts of the grid become harder to observe with precision. Operators act more cautiously, and if a separate equipment failure happens during the outage, diagnosing it may take longer. A blackout is not guaranteed, but the safety margin becomes thinner. By sunset, the largest damage is not a dramatic collapse, it is accumulated delay. Trucks miss warehouse appointments. Warehouses cannot predict arrivals as accurately. Flights, ships, emergency calls, repair crews, and deliveries form queues. A delayed component reaches a factory late. A refrigerated shipment spends longer in traffic. A maintenance team takes extra time to find a remote fault. Each problem is manageable alone, but modern logistics depends on thousands of small events arriving in the correct place at the correct moment. Supermarkets would not become empty in one day. Society would not suddenly return to the Stone Age. Instead, the world would become older by a few decades, more manual, less efficient, and much more dependent on human judgment.
Police officers direct traffic where congestion becomes dangerous. Pilots and sailors use procedures that feel old-fashioned but still work. Dispatchers ask callers for landmarks. Drivers unfold paper maps or photograph public ones. Radio instructions become valuable again. Strangers begin giving one another directions. Alex eventually reaches home not because his phone recovers, but because he follows road signs and asks a person at a gas station which bridge to take. Then, exactly 24 hours after the outage began, the signals return. Alex's blue dot jumps back onto the road. Phones reacquire satellites. But the world does not reset instantly. Safety-critical operators first confirm that the signal is genuine and stable. Networks carefully synchronize their clocks. Airports and ports still have queues to clear. Companies must reconcile delayed deliveries, missing location records, and timestamps created by drifting systems.
The outage is over, but some of its effects continue into the next day. And that may be the most surprising lesson. GPS is not just a voice telling Alex where to turn. It is an invisible global agreement shared by billions of machines. This is where you are, and this is the exact second you are there. If that agreement vanished for 24 hours, civilization would not collapse, it would bend. It would slow down. It would become less automatic and more human. The strangest discovery would not be how easily we can get lost. It would be how much of the modern world keeps moving only because everything agrees on the same place and the same time. What do you think would cause the biggest problem during those 24 hours? Tell me in the comments. And if you enjoy exploring strange what-if scenarios like this, subscribe to the channel.